Internal direct products. As we have seen, the external direct product provides a method of putting groups together to get a larger group in such a way that we can determine many properties of the larger group from the properties of the component pieces. For example, if G is the external direct product of H and K, then the order of G is the product of the orders of H and K. Every element of G has the form order pair HK, where H is in the first group, K is in the second group. If the order of H and K and the order of K are finite, then the order of the pair HK is the LCM of the order of H and the order of K. If H and K are a billion, then G is a billion. If H and K are cyclic, then the order of H and the order of K are relatively prime, then the external direct product of H and K is cyclic. It will be quite useful to be able to reverse this process. That is, to be able to start with a large group G and break it down into products of subgroups in such a way that we could glean many properties of G from properties of the common component pieces. It is occasionally possible to do this, but not for every group G. Definition. Internal direct product of H and K. We say that a group G is the internal direct product of H and K, and we write G equals H times K. If H and K are normal subgroups of G, and G is equal to H times K, this is the set of all products of elements from H and K, and the intersection of H and K is just the set of this trivial set consisting of the unit of the group E. The wording of the phrase internal direct product is easy to justify. We want to call G the internal direct product of H and K if H and K are subgroups of G, and G is naturally isomorphic to the external direct product of H and K. One forms the internal direct product by starting with a group G and then proceeding to find two subgroups H and K within G, such that G is isomorphic to the external direct product of H and K. On the other hand, one forms an external direct product by starting with any two groups H and K, related or not, and proceeding to produce the larger group, the external direct product of H and K. The difference between the two products is that the internal direct product can be formed within G itself using the subgroups of G and the operation of G, whereas the external direct product can be formed with totally unrelated groups by creating a new set and a new operation. So, in the second case, G, the group G is not given in the beginning. So for internal direct product, the group G is given, and then we find H and K inside G, normal subgroups, whose intersection is just on the element E. And for external direct product, we start with two given group unrelated, H and K, and we form the set of all ordered pairs, HK. Example 18. In the dihedral group D6, which has order 12, let F denote some reflection, and let RK denotes a rotation of k degrees counterclockwise. Then D6 is internal direct product of these two normal subgroups. These subsets are subgroups, and each of them is a normal subgroup of D6. We know that this group R, not R180, is actually the center of D6. For example, R60 is not present here or here, but R60 can be obtained this way. Multiply R120 by R180, you get R300, and the inverse of R300 is R60. Student should be cautioned about the necessity of having all conditions of the definition of internal direct product satisfied to ensure that H times K, the set of all multiples of this kind, is isomorphic to the set of all to this external direct product. That is, if some of the conditions for internal direct product are missing, then this isomorphism will not be in place. For example, if G is the symmetric group S3, and H is the cyclic group generated by the permutation 1, 2, 3, and K is the cyclic group generated by the transposition 1, 2, then indeed G is equal to H times K, because every element of G can be written as a product power of 1, 2, 3, and a power of 1, 2. And the intersection of H and K is trivial, the identity map, but G is not isomorphic to the external direct product, since the external direct product is cyclic, because H and K each is cyclic group, this of order 3 and this of order 2. 2 and 3 are relatively prime, so the result is a cyclic group of order 6. Whereas S3 is not cyclic, it is not abelian. So these groups HK and H plus K are not isomorphic, but it is because K, the second group, is not normal in this case. So one of the requirements for internal direct product is not met. Internal direct product can be defined for H subgroups. The definition is given here. it is a little bit more complicated. And we have this theorem in place. If a group G is the internal direct product of a finite number of subgroups, H1, H2, and so on, Hn, then G is isomorphic to the external direct product of H1, H2, and so on, Hn.